Welcome, and we're going to look at implicit functions and how to differentiate them. So we should probably understand what an implicit function is and then how to differentiate it, right? So what is an implicit function? Well, you can Google that. But most of the functions that we've encountered up to this point have been functions of a single variable. Okay, and also typically the degree of the dependent variable is isolated and the independent variable. So the dependent variable again is y, and the independent variable is x, if you want to think about it that way. But we've always had cases where it is y equals something, right? There might not be that opportunity for us. So for instance, the dependent variable is not degree 1. So we notice we have y squared. What do we do in that case? Can we still find its derivative? Is the derivative defined? And then another instance is, well, we can't isolate it even if we are able to say, yes, we can still take the derivative. We're not able to isolate it, so how do we do the product rule, quotient rule, all that sort of thing, okay? Or you could have a combination of that, okay? And these types of functions, each one of these, are called implicit functions, where we don't have a function defined explicitly, meaning like y equals, but there is some algebraic relationship between the two, okay? And that's from Wolfram. All right, the first one that we saw, this first example, you might recognize that, or I hope you recognize that, as the equation of a circle of radius 5 centered at the origin. And we're actually going to look at that thing. So can we differentiate this? So I mean, it isn't a function in its outright. It is an implicit function. We could create this into a function by defining it in pieces. We'll talk about that. But our problem is that we want to find the tangent lines to the function below. And so is this continuous? Well, yeah, kinda. Is that necessary for differentiation? Not necessarily. But we know that if it does have discontinuities, that generally means it is not differentiable. Okay, so to do this traditionally, what we would have to do is isolate y, and we can do that. Move the x squared to the other side, square root both sides, and then we have to account for the, since we introduced a square root, we need to include a plus and minus, okay? And then we can certainly find the derivative, dy dx. I'm going to use that instead of y prime. Either one is equivalent, but then we would get plus and minus, and I'm skipping a lot of work, like you'd have to do the chain rule and blah, blah, blah. You end up getting plus and minus x over square root of 25 minus x squared. Okay, and then you can go on and, sub in 4, find, and to get the slope, and then do the tangent line, blah, blah, blah. Okay, yes, we get the point, we can do that. Okay, now this works using the traditional method for this particular exercise, but in some of the other instances, you can't. Okay, so what we're going to use is a method called implicit differentiation. Effectively, our rules of power rule, product, quotient rule, chain rule, they all still hold, but the key difference is that we're differentiating a variable other than the independent variable, so other than x, with respect to that independent variable. Okay, and we use the chain rule here. Okay, and you can see my comment here about, in practical terms, we are differentiating with respect to x, but whenever we differentiate y, we have to include the dy dx because of the chain rule. Okay, so let's see this in action. So we started with the equation x squared plus y squared is equal to 25. Under implicit differentiation, what we would do is apply the operator dy dx to both sides of the equation. Okay, so this means we would differentiate everything with respect to x. Okay, formally, according to the chain rule, we would, so for the left-hand side, we remember that the derivative is a linear operator, so you can move it and apply it to both things. So we'd have d dx of x squared. Now this is notation, I'll explain it in a moment. and then d dx of y squared, and then we'd have d dx of 25 on the right-hand side. Okay, right-hand side is, well, let me go through these one at a time. So now what this is saying is we need to differentiate x squared with respect to x. So we would operate as normal. Derivative of x squared is 2x, and then according to the chain rule, I would have to, so I would bring the power down, and then I have to differentiate x with respect to x. This is effectively 1. Okay, you'll see that in the next step. Now where things get interesting, is this next step. So I can still differentiate y as normal, and this is kind of weird, but it would just use the power rule. But now I'm not differentiating x, or I'm not differentiating y, I'm differentiating x. So according to the chain rule, I have to have dy dx. Okay, so this is the new part. We're differentiating some variable expression that is not x. So we need to include that dy dx in there as well. When we do this last one, we just get 0. Okay, and so now simplifying this, derivative of a constant is 0, that's why the right-hand side is 0. Okay, this whole thing is effectively 1, so simplifying, I can write this as 2x plus 2y is times dy dx is equal to 0, and the point of all this is I want to find dy dx, right? I want to find the derivative of y in terms of x, so I need to isolate this. If I isolate that, okay, move the 2x over, I'm going to come up here to continue, so that I have 2y dy dx is equal to negative 2x. Okay, and then when I isolate dy dx formally, I get negative 2x over 2y, or simply put, I can just say negative x over y. Now, if we take a look at this, is this the same thing as what we got above? So I got negative x over y. Here I got negative x over square root of 25 minus x squared. Okay. It actually is the same, right? Because y is the same as the square root of all that. So I could rewrite this as plus or minus x over y, and the plus and minus was a consequence of the square root, so we actually, and this should be minus plus, I forgot to write that down, but if you absorb the plus and minus with the y, we would end up having a minus y, or minus x over y. Again, you have to go through the math to do that formally, but you do end up getting the same negative y over x. Just by implicit differentiation, it might come out a little neater. Okay. Now, this whole concept of including dy dx, that's new, and that's a little weird. So in the videos that follow, we're going to get a lot of practice identifying this dy dx and solving for it.